Hey guys, in this lab we're in Module E, Week 2, and we're going to be dealing with Mohr's Circle. And before we get into Mohr's Circle, we are going to talk about what is torque, because the problem we're going to be using is a torsion problem. Another problem you're going to have is a air can that you're going to fill up, and it's going to be a similar problem. I'm going to focus this presentation on the torsion one. Now, you're going to be able to take the same strain values and create a Mohr circle just like we did on this one for the shaft and torsion for the can of air. Now let's talk about torque to get us started here. Torque is force times distance. So you're going to have a big wrench you're going to put on a shaft. We're going to have a nut welded on the end. So we want to make sure that wrench doesn't fall off. And at some distance, we're going to put a load. Now that load is going to come at some distance. So we need to measure the exact distance from the center, the linear distance coming out here. Your wrench may be up at an angle and the weight coming straight down. So we want to get that linear distance, the correct distance there. This one's nice and straight for us. So we can find that the force and the distance on these two are both going to have the same torque because we have different load values here. So the further you reach out, the less you have to pull on this. So we know the torque equation, and all these equations are going to be in your lab sheets as well. This is just a good review to help you out with a little bit with Mohrs circle. Now, what is torsional shear stress? Just a quick refresher. Tau max is always TC over J. Now you're going to see some books have R's here instead of a C, or you might even see a Y. We need to know that those are all interchangeable because R is the radius. Okay. Now, this is the maximum shear stress. That's going to happen on the outer portion of the shaft. That's our torque. The radius is the C, and then we have our polar moment of inertia here. Now, the first thing I want to point out is when we have a shaft and we have a stress element on here, it's going to look like this. When we put our shear onto it due to torsional loading of this shaft, we're going to see it deform at some angles here. And we're going to have shear stresses, and that's going to be our maximum stress in this element. And we're really interested in that so we can compare that value to the material properties and find out if it's going to yield or not. Now, if I look over here, we have a pool noodle, and before we put it in a torsional loading, we drew a square on here. When we put it in torsional load, we can see how that stress element distorted there, looking much like this. Now, what is polar moment of inertia? You guys have a hollow shaft, and you're going to use this equation right here. And that is going to give us the properties of this shaft in torsion, and it is going to represent our stress distribution, which the highest stress is on the outer surface of that shaft. That's tau max, TC over J. So that's where we're going to mount our strain gauges for this activity, is on the outer diameter, the furthest out on the radius, and we're going to be able to make calculations for maximum stress there. Now then, let's think about this. We're putting strain gauges on this shaft, and we're going to be able to draw a stressed element for this. Now, we're going to convert the strain values we get on our strain gauge unit from those strain gauges. We're going to convert it over to the values we're going to convert those over to stress. And once we get the stress values, we're going to go do a Mohrs circle. And what we're going to find here, and I have it here, we're going to find maximum principal stresses and maximum shear stresses. Now, I'm not worried about calculating the angles. In strengths and machine elements, you're going to have to do that. For this lab, we're just interested in the maximum principal stresses and the maximum shear stress. And these are kind of two things that we're going to learn how to calculate and draw our Mohrs circle for. Now, in your lab sheet, you guys will be doing some calculations leveraging some of the equations to compare your Mohrs circle and expected values. And these are equations that would come out of your strengths book or the machine elements book. So we could calculate our principal stresses. That would be sigma 1 and sigma 2. So we need to remember that maximum principal stresses are sigma 1 and sigma 2, and we're going to be able to come in here and calculate them. So the stresses in the X and the Y directions and our shear stress that we're going to see on here, that's going to be our gauge that off at a different angle. This one is going to line up. The stress X is going to go lengthwise with the shaft, and then at 90 degrees, we're going to have our stress on the Y. And we're going to calculate those from the strain values, okay? We're going to put them in these equations. We're going to calculate sigma 1 and 2. but we need to draw a Mohr circle as well because it's part of this activity is to cement not just the equations, but the concept of Mohr circle. Now, one of the other equations we're going to be leveraging is sigma average. We can come in here and add these up and divide them by 2. We're going to do that on Mohr circle. And then we're going to be able to come in here and calculate our tau max by equations, or we're going to be able to recognize that directly off of the Mohr circle. Now let's talk about this Mohr circle. Different kind of loadings can have different Mohr's circle. And Mohr's circle is going to represent a graphical method of showing our stresses on that element. So our stress in the X and the Y and our shear stresses. If I was in pure tensile loading here, uniaxial loading, I would expect to see my circle coming much like this, where here's the shear stress, and these are my normal stresses right here, my sigma 1 and 2. I'm going to see these things coming in here, and this is going to meet up with 0, and we're going to be off of here at some distance. If I'm compressing this, the circle is flipping over on the other side of the shear stress line and looking like this. So we can see if we have tensile or compressive loads getting into our samples. We're going to be doing pure torsion or pure shear, and we're going to be twisting that shaft, and we expect to see the rotation of our stress element. When we do that, our circle should be about the 0, 0 point here. And now in real life, in our application we might see it adjusted off a little bit. That's okay, because the way we're loading it, there could be slight loading on there, but we're going to still calculate those, and the way we do it with Mohr circle, it's going to take in those odd stresses that maybe isn't just pure shear or torsion, that we might have some other stresses on there. It's going to take that into effect with our values doing this Mohr circle. Now, we're going to have strain gauges on your sample, and you're going to, on your sheet, we need to talk about how we're going to hook these up to our stress indicator equipment. On your shaft, you're going to have 2 sets. One is going to be on a 45-degree pattern. Another one is going to be on a 60-degree pattern. They're going to be labeled A, B, C. A is going about the x-axis. So this is the direction the shaft is going to be running, okay? And we're going to put the torsion going about that x-axis. So C's are going to represent our y-axis here. This is going to be our stress at an angle measuring our shear stress, okay? Now then, we're going to have to convert the strain gauge values that we collect from those. Okay, now how are we going to collect them? We're going to hook this gauge right here on the 45-degree pattern to channel 1. And on your lab sheet, it should show that. This is going to be channel 2, channel 3, channel 4, 5, and 6. So we want to keep track of those channels. We're going to be able to get the strain values on those, and we're going to be able to calculate the stresses related to those elements. Now this is an example of a Mohr circle. Yes, you need to hand in on engineering paper, a handwritten, you're going to use a ruler, protractor, make it look nice, a Mohrs circle. Let's say that I had gone out and I calculated my stresses in the X, the Y, and my shear stress on a stress element due to torsion or some kind of loading. Okay, we need to draw a Mohrs circle. So the solution, and I've got notes on here as reminders to kind of help you because some of you have done this, some of you are probably getting to be doing it at the end of the semester. So if you need extra help doing Mohrs circle, come see me. I'm probably going to be a little bit more helpful on Mohrs circle than possibly some of the TAs on this. When we draw the Mohrs circle, we want to do it in a very systematic approach here. Now, I could draw the original stress element. You guys don't have to do that, but I like to draw this thing. In some courses, you would be expected to draw that. We're not doing that on this lab, but I'm going to label those forces. So in the X direction, we had a positive 20 pounds. That was a tensile type load maybe. In this direction, we have a compressive load in the Y because it was negative. So I drew it negative and I listed it positive here because I know the arrow is going negative. Okay. Now then, this is the hard one. How do I draw the arrows for my shear stress on this element? I've got this little reminder over here. This really helps out because we're going to need this for the Mohrs circle. If it is negative, then it wants to rotate clockwise about that axis. So if I look at the x-axis here, we had a -8. It's going to want to rotate clockwise, and that's the way I know to draw that arrow. Now the convention is arrowheads on the other three sides of the square are going to be head to head and tail to tail. So I can just draw those. If I wanted to start with Y and I was going to go about the Y-axis negative, then I would know I could draw that arrow and I could do the same thing head to head. So on a graph paper, you're going to come in here and draw a coordinate system up. Take our stress element here and draw it. So let's talk about how to plot this point right here. We have the 20 megapascals right here, and about this face, it's wanting to rotate this element in this direction. Okay, now this is kind of odd because you're going to think I need to use these to do what we're going to do in the plot. This little rule we had up here was for how we draw the stress element. What I like to look at is just on the face, on the X, it's trying to rotate the element in a clockwise manner. So this arrow right here is going to represent that rotation. So we're going to be on this side. Likewise, if I go over here to the Y axis, it is trying to rotate in this direction, a counterclockwise method. So that's where we're plotting. This is counterclockwise. So X is coming over 20, and we're going to go to this 8. Y is going to go over here to minus 10, and because it was trying to go counterclockwise, we're going to come down to this side. That is a little bit tricky in how to establish the X and the Y on your graphs. Let's talk about step 4 here. Once we have those 2 points plotted, we're going to draw a line that connects the two. Where it intersects this line, this stress line, that is going to be our sigma average. We could read it off the graph, and we're going to come out with 5 megapascals, and there it is. The next thing we need to do is we need to calculate the maximum shear stress, tau max. That is going to be the radius of the circle. So when we do that, we need to come in here, and I'm going to kind of move up here. We need to find out the radius of this circle. What is the radius? Well, we know the distance from here because we know this is 5, and we know this point being 20. We're going to come up and hit that arc and draw a line. We got this nice yellow triangle here, so we know that this here to here is 15, and from here to here is 8. We can now come in and do simple trig and calculate the radius of that shaft. That's going to be tau max. So you need that on your lab sheets, guys, and you need to show how you calculated that. This is why we want to graph it to scale and show everything on here. The next thing we need to do is while we have that graph, and I'm just kind of putting this up here, I'm going to find sigma 1 and sigma 2. And we're really not worried about the angles on here. I've got this all shown on there, but our angles for those two are going to be right here. What we're after is basically on this lab right here, sigma 1 and sigma 2. Those are going to be our stress levels that we need to calculate for sigma 1 and sigma 2. How do we find those out? Well, basically, we know this point, and we know the length, the radius. We can come in here, which our radius is 17 megapascals on this axis from here to here. So we know the distance here to here. We can come in here and calculate the line distance from here to here, and that's what we've done here for both sigma 1 and sigma 2. That is going to give us these two values of these lines here. Now then, in strengths and machine elements, you're probably going to come back and redraw the stress element in terms of its principal and maximum shear orientations. We're not going to require that in this course. What I'm after is the maximum shear stress, sigma 1 and sigma 2 here on this axis. So this would be your Mohrs circle for this.